Schnormeyer. I'm the Associate Dean for Advising in the College of Arts and Sciences, and I'm also coordinating the Haddin Forums this semester. So it's my pleasure to welcome you. As I said, the sign-up sheet's going around, so please sign in if you haven't. I've got handouts for the future forums. We've got 2 more left this year. And I'd like to ask Dr. Rudy Weipert from Math to go ahead and introduce our speaker today.
Thank you very much. Okay, welcome everybody here. Of course, today is a gorgeous day, and I didn't have any trouble coming. So, our speaker today will be Dr. Carmeliza Navasca. She got her PhD in 2002 from the University of Davis, University of California at Davis, and then she spent several years in various postdocs. She was in Canada at Waterloo. She was at UCLA for 3 years, I think.
Yes.
She was in France at the CNRS. That was one other place. She was a year at Rochester, I think. Rochester Institute of Technology. And then she went to Clarkson University in Potsdam, New York. And she was there until 2012, and we were extremely lucky to lure her down here. We promised her there is never ice or snow. And that, of course, was a compelling argument for her. And here she is. And she has an interesting title about fast multiplication and what math.
Okay. Thank you, Rudy, for the introduction. So the title of my talk is Go Forth and Fast Multiply, and there's actually 2 titles. What's math got to do with it? So it's really about an introduction to applied mathematics. What do I work on a daily basis besides teaching calculus and other math courses? So it was kind of difficult to prepare for this talk because my goal was not to put any math equation on any of the slides, but I had failed to do that. So there's 1 or 2 slides with math equations, but that's for the math audience. So, okay. All right, so I'm going to begin. So, first slide is an image is a matrix. Okay, so this is, I stole this picture. This is Mapplethorpe's photo of a parrot tulip. So this is an image, which is really, an image is a matrix filled with values, okay? So before I begin with I go into the next slide. So every day I tend to work with 3-dimensional matrices, two-ways arrays. But today, today I'm going to unfold this cube into a matrix. So a matrix is really, you can think of it as, so I unfolded it the wrong way. So it's a matrix is made up of columns of data. So these are 2 columns put together. Or you can think of them as columns, vectors of columns or rows concatenated with data. You can think of these blocks as our values. Okay, so that's the matrix. It has rows and it has columns. Okay, for me, my world is basically I see everything as a column, but now I'm teaching calculus 2 where we teach vectors. The books have it in row vector because I guess to save space, right? So I kind of have difficulty. I always write everything in columns. Okay. So I was anticipating some people from humanities, and I had to relate this talk to some literature, and all I could think of is that's my work is really exciting, you know. So what do I mean by 256 shades of gray? So we saw an image here, a photo, and basically an image is made up of many pixels represented by numerical values. In this case, I'm choosing the values from 0 to 255. This has to do with an 8-bit integer. You can have more. So in fact, you can have 2 to the 16 minus 1 shades of gray if you want. Okay. So this is a huge matrix, actually. So what I did is sort of draw a red box, kind of centered around the tulips and the stem. And I zoomed in to see what are the actual values in that little box. And even then, I had to zoom in a little bit further in because the data is quite huge. And so what happens usually is you chop your image into many columns and many rows. So you create there are a bunch of pixels. Okay, so you end up with little squares, which are called pixels, and they have a numerical values. And the values range from 0 to 255. So in this case, 255 is the color white. So you can then go from, oops. All right, so you can see the values here range between 0 to 255, and that kind of represents just that, actually just not the whole picture that you're seeing, the pixelated picture you're seeing there, but just kind of a portion of that, okay? So I like to image process beautiful photograph while my students, Ali and Nicole and Christina, like to image process tumors, things of that nature, which I can't blood vessels, things I cannot look at on a daily basis. So I download beautiful picture of Mapplethorpe or whoever, O'Keeffe or any of the other artists.
Could you tell us just what one of those values is?
Oh, thank you. So 0 to 255, sort of the intensity of the color. So 255 means the color black. So if I go 254, it's a little bit off of, yeah, so 0 is completely white. Okay, so there's this many shades, but in fact you can get more, depending on how many bit you have. So there's actually, you can go up to 2 to the 16th shades of gray, minus 1 shades of gray, depending on how much storage you have. But on a regular, standard image, it's 256 shades, different intensity.
Okay.
Right.
Thank you.
So you can take any photo, you can download it from the internet, upload it, and you can do a bunch of, you could see the actual values in your photo.
So the color codes comes in addition to that.
Yes.
Which is colored.
The colored one is kind of interesting. So the color actually comes in as a tensor. A tensor is, it's made out of 3 matrices, 3 layers. So you have the red intensity, how much red you have, how much green you have, and how much blue you have. But you're only seeing all of them put together as one. But when you actually see the data, there are 3 layers. Okay. Okay. So let's move on to another example. Sound signals are matrices. So if you want, so I found this video on YouTube. So if you want to play it, you will hear the song by the Beatles, "All You Need Is Love." And I'm not, I guess, I won't play it during the talk, but maybe later on if you want to see it. What you're seeing is actually, once the song is being played, there's a red line that's going through, and it's showing you the sound signal at that point. So what you're seeing here besides the image, is this thing, this matrix here. And that matrix is called a spectrogram. Okay, so what is it? So this x-axis is time. So the song is actually just, I don't know, a minute long, I think. And the y-axis is the frequency. So what does that represent? So a lot of you are a musician here. So for that split second, this column here, this color represents the intensity of the frequency available, being played at that time. Okay, so the colors, I checked, I think blue is high frequency and reddish tends to be low frequency. Okay, for this song, I think you see a lot of red and pink. I guess I could have picked blue and yellow, but I didn't because I like this song. So anyway, so this is only for a few seconds, so this is a very, very long matrix, so it kind of moves. And so this represents just a part of the song. Actually, maybe it's not part of, maybe it's a full song, but so anyway, so it's a very, very long matrix. So if you want to process sound signal, this is one way we sort of work with signal. So what you hear, this is what are the numerical representation of sounds. Okay, so the previous slides are what you can see, right? Can be represented a matrix. So this slide's what you can hear can be represented as a matrix. Okay, and there's a lot of things we could do with this spectrogram. So in fact, you can pretty much from the sample of data, we have technology in which we can pretty much determine what instruments are being played from this spectrogram. We can demix it and say, look, I watched the video, there was a trombone and a trumpet in there as well as drums, so there's a mixture of an instrument collected in this data. Okay. So for a lot of maybe scientists and engineers sitting in this room, this is more or less the type of data that we're familiar with. So you're looking at, so there are a lot of mathematical equations. They're called partial differential equations. And when you want to solve them numerically, these types of equations appear. And so this is a picture of a sparse matrix. So what's a sparse matrix? We're actually looking at a photo or a picture of a matrix in which, in this case, we have the values, the blue dot represents the non-zero values, and the non-colored dots are the zero values. So we say a matrix is sparse if there are significantly more than non-zero entries in our matrix. Okay, and most of the time in these type of mathematical equations, we see sparsity in a lot of matrices. Okay, and once we have a matrix like this, we need to do a lot of things on it. We need to maybe multiply two of these. Maybe we need to invert, whatever that means, some of these matrices. And equations involve these matrices. So some of you have taken linear algebra maybe. If you're given a linear system and you're given a matrix A, that's your matrix A, and your A inverse could look like this. Okay? So, and a lot of these partial differential equation, mathematical equations, boils down to solving a linear system in which the matrix looks like this. Okay? And it's actually very, because the sizes are huge, so you want techniques in which you can quickly invert this or somehow solve this linear system involving this type of structure. Okay. So they appear, these equations have application in mechanical system and electrical system. In fact, I think I stole this from a problem of studying airflow around an airfoil. So an airfoil is sort of the cross-section of an airplane wing. So this is a subject in computational fluids dynamics. And so if you're on the plane, you see a lot of turbulence. So engineers are working on this type of problem so that it improves the design of an airplane wing, okay, by knowing simulation of the airflow. Okay,
What is the typical order of magnitude of the size? Is it big?
Huh?
It's big? Is that
Yes,
big? So
it could range from, depending what dimension you're in. Some people study 2-dimension or 3-dimension. So it could go high, PDE, I mean a PDE.
but I meant the size.
Oh,
of
the size.
Or the
The size, yes.
specifics.
So it could go high as 1,000 to 1,000,000. So you need to solve this perhaps iteratively and many times. So you need a way to solve or invert 1,000,000 by 1,000,000 matrices, however many iterations you need.
So how often do you ask your students in linear algebra to invert 1,000,000 by 1,000,000?
Never. A 2 by 2. Maybe I could give it as an extra credit, and perhaps whoever has a solution can open up a business after that, sell their ideas. So,
Sell airplane wings.
huh?
They can sell airplane wings.
Oh, sure, yes. So this is another example. So I noticed some people from chemistry. This is a picture of what we breathe. Air pollution is something we breathe, and they can be represented by matrices. And so for the last few days, so Rudy was saying that we lived in New York for the last 5-6 years, and so we were complaining that there's no salt. And then I'm thinking, we don't need salt because salt actually is a bad air pollutant. So, so this, what we're seeing here is a matrix, and kind of difficult to see. So on top is all the chemicals, but only a few of them, I only represent a few of them, like magnesium, aluminum, silicon, sulfur, fluorine, and I don't know what A stand for, the chemist can't see. So anyway, those are the chemical species and the concentration, okay? And these factors, factor 1, 2, 3, 4, and 1, 2, 3, 4, 5 are the pollution. So I believe, my notes, that the pollution we're looking at is soil. The first factor is soil. Second factor is salt. The third factor is the pollution emitted by airplane as it lands. And then 4 or 5 are type of sulfur. And so this is actual real data from my work. So I collaborated with someone who sits in the advisory committee of the Environmental Protection Agency, and he's actually using our algorithm to sort of to kind of curve emission standards for the U.S.
What is on the horizontal axis?
Horizontal.
No, horizontal.
This one.
Yes.
These are chemicals, magnesium, the amount of concentration. So these are the chemicals in the air. And so what happens is, so you have to identify, so they collected the fun part. We don't do the fun part. We don't do the collection. We just get a bunch of data, right? We get an email of data. So we have a set of data. And sort of, we can use our method to be able to get a picture like this. And so the expertise of a chemist would be able to identify that this is sulfur. I can't do that. I don't have the experience or the eye to do that. And I've asked him if there's a book that I can check. This is sulfur and this is soil. And he said there is no book written, but it's just his 30 years of experience of.
Okay, those are the chemicals. What are the colors up there?
The colors.
The brown, yellow scale.
So those are the sizes, the sizes of the particle. So it's actually, so what I'm saying, this is also kind of there's a tensor, this is a tensor structure, but I'm not, I'm just gonna view it as a matrix. So for one thing about your question, if you have, it matters about the sizes of the molecule because which one that could bind, right? So, so if if you don't take a note of the different sizes of the particle, then you sort of don't have an idea of I mean, for a chemist, won't be able to say, well, this sulfur is sort of combining with soil, it's resuspended in the air, and so forth. So it gives the scientists more information. Oops. So the first one is soil. Did I say soil? Yes, soil and salt. So salt is, this is actually data taken from the Dallas airport. Okay, so a lot of you fly to DC and probably go to one of the two airports. And in fact, we know that, it's known that they actually don't use salt, they use sand. And so this factor 2 actually carried by the airplanes. So it was not actually because they don't use salt in DC also. So this is carried by the planes themselves. And factor 3 comes from, what is 3 again? 3 is just the particle emitted by the airplane as it lands. And then 4 and 5, the two different types of sulfur. 5, they can detect that it's coming from local vehicle with diesel. So they can detect that. And this seems like sulfur that sort of combined with the resuspended soil. Okay, so they can tell all of these things by just these plots. So the air we breathe are also represented by matrices. Okay. So what we can process, what's given to us again, is just a collection of data of mixed particles taken from a 3-month period. And then with the type of algorithms we have, we can sort of identify the different pollution in the air. Okay. All right. So those are the different types of matrices that sort of that we can sort of see and hear and breathe. And there are actually a lot more matrices around us. So now I'm actually going to sort of start talking about, so once we have these matrices, what do we do with these matrices? Okay, how do we come up with algorithms, given the data that we have, given the matrices we have, what can we do with them? Okay, and so what I work on is to come up with numerical algorithms that can analyze these data, okay, for images. So as I mentioned, my student likes to image process maybe MRI scan. Why do they want to play with that? Well, it's very expensive to have an MRI scan. And not a lot of the times the patient move around, and so you can't detect perhaps, is that a tumor or is just some kind of error. Okay, so we create tools that will remove these artifacts. Okay, we can create tools that will compress your data. Okay, through algorithms, and a lot of these algorithms involves many operations, but one of the things that's common in a lot of algorithms is matrix multiplication, just basic multiplication of these two matrices. Okay, so you now have images and sounds and even air matrices. Okay, so but before I talk about matrix multiplication, I'm going to tell you about the prerequisite to learn matrix multiplication and fast matrix multiplication. So multiplication table, so we learned this in grade school. So I don't have calculators that are fancy these days where, my students have really fancy calculators. So I have this in my office. So if I forget to multiply two numbers, I consult the educated monkey. So, so there are fancy calculators there. So if you forget your multiplication table, I have this. People have calculators. This is simply my calculator. Because I honestly cannot, with the technology we have today, I don't even know how to turn on a calculator. So it's, and then let me remind you what are arithmetic operations that we need. So we know how to subtract, we know how to add, subtract, multiply, and divide. So those are the basic arithmetic operations. So what we're going to do is understand the complexity of matrix multiplication. So, like I said, I tried to, the color blue didn't come out here, but I have other squares there that are, I think you could see the outline. So this is my poor attempt of trying not to write a math equation, but my husband said this is a math equation. So, so what is this? So these are, instead of these fancy images that I had on the previous slides, I just have basic dots or squares that represent the value of the matrix. And so what I'm showing here, what's exactly happening is that, so remember I said a matrix is really a concatenation of columns or row, and we often count the number of rows we have, and we count the number of columns we have, and that tells you the size. Okay, so if you have 3 columns, you have 3 rows and 3 columns, then that's what we say a 3 by 3 matrix. Okay, so in order to multiply 2 matrices, so one thing has to agree is that the column number of the first matrix has to agree with the number of row for this matrix. So that because I'm about to define matrix multiplication, so that's what's needed, because if you're trying to calculate the product of 2 matrices, you're going to get another matrix, and you have these values on the matrices, and these values are going to come from a combination of the values of the 2 matrices that you're multiplying. Okay, so for a 3 by 3 times a 3 by 3, you're going to get a 3 by 3 matrix. And so how do you calculate the element right in the middle? The element right in the middle sits on the second row and sits on the second column. Okay, so what you're going to do, you're going to take the second row of the first matrix and the second column of the second matrix. And the way you come up with a value on this side is to just match all the yellow values and the orange value and the red value. You multiply the 2 colors together by using this, or you know your multiplication very well. You don't need to consult with the educated monkey. So you multiply them, and then you add. And so what you end up having is this the combination of all these colors, right? When you're adding them, the values together. Okay, and so you do that. You have to do that for every missing spot on for this matrix here. Okay, so that's a lot of computation only for a 3 by 3 matrices, but the matrices I've shown you in the previous slides are far more than 3 by 3. Okay, So for the first image, that's at least 500 by 500. So that means I have, for the image of the tulip, that's about, you can say about approximately 500 by 500 pixels. So that's 500 rows and 500 columns. Okay, so that's a lot of multiplication. And
Times 500 multiplications.
yes,
The
so
cube, 500 cube.
yes, so I'm about to go to that. So, okay, so the next slide has more equations. So, so this is what you call a 2 by 2 matrix multiplication. And so we're looking at a matrix here of just 2 columns, 2 rows and 2 columns. And our goal is to multiply them, right? So now we don't have colors, we don't have block. And instead of a numerical value, we're just going to put some variables. So I'm going to call that spot A11, the second spot A21, the very top of the second column A12, and then the element below that's A22. Okay. So if you want to see how the numbers are arranged, the first number represents the row number, and the second number represents the column number. So that's how you can sort of find your element. So if you were to say, which element are you interested in? Well, it's the second column, the second row and second column. Okay. So again, that's basically how you come up when you're multiplying a 2 by 2 matrix, 2 matrices, then you're going to get a 2 by 2 matrix. And this element is exactly this image here, where you just take, to get the C11, you take the first row, A11, A12, and then you need to multiply that with the first column, B11 to 12. That's exactly what we're doing for every single spot. Okay. Everyone's good with this. So if we count the number of multiplication, so how many multiplication do we have to do? There are 8 of them, or 8 of them, just for a 2 by 2, for a 2 by 2 matrix multiplication. And how many addition that we have to do? 4. Okay. So that's for a 2 by 2, that's quite a bit. And n here could be any number of your choice, but if you have the data that I've shown you in the previous slide, those data are huge. They're not 3 by 3. They're at least 500 by 500, or even think about 100 by 100. So 100 by 100 matrix multiplication is how many multiplication you're going to do, 100 to the 3 multiplication, and how many addition? Well, that's 100 to the 3rd minus 100 squared addition. Okay, so that's quite a bit, yes.
Now, why are you multiplying the matrix?
Why am I multiplying the matrix? Oh, that's a good question. Because in a lot of the algorithms, so once you have a data, we have a black box. That black box contains some algorithm that requires matrix multiplication. And a lot of the algorithms that we produce, we can't go around it. So people make a living trying ways to speed it up or find a method to go around it. But one way to solve it is maybe improve the algorithm of not trying to get a better way of finding a formula for matrix multiplication that's going to require less multiplication and addition. But yes, so these black box contains algorithms which requires multiplication of matrices. So anything you do with a given data, it has to be processed, it has to be analyzed. And the way we analyze it is, one way is through numerical algorithms or methods, which is a set of instruction that we feed in to the computer and say, do a bunch of these steps. And at the end, we get more matrices. And then, so then we can translate this data into picture or sounds and so forth, however you want to represent the data that you get out of these methods. Okay.
So the image of the tulips represents a matrix, a single matrix
Yes.
with a number of elements.
Yes.
So under what conditions would I want to multiply that with the matrix? Would it be, to say darken it or something, or would I multiply two images of tulips?
Yeah, so
together,
there's
or-
ways that maybe the image you got is kind of, it's not clear, it's not a good resolution. There's de-blurring, there's ways to make your matrix kind of smoother, but lessen the sharpening. You don't, if you want your image to be smooth, then it's less sharp. So you could do this by smoothing your data. Okay, so what's a good example?
I'm just trying to figure out what would motivate you to
Yeah, so
multiply two matrices together for image processing in some ways, what I'm not following.
For image processing,
Well, the tulip example, or even the chemistry example, right? Each of those elements contains, I think, if I
So-
understand the matrix correctly, represents
yes,
concentration, element type, as well as where
Yes.
it's located.
yes. So one way in image processing is probably data compression. Okay, so data compression is sort of, so whenever you download an image, say, how do you want this to be, what quality, right? There's percentage that you click, okay? So we can do this in terms of, so we can represent this image by simple matrices that are product of other matrices, and from there we can do some reduction. Okay, so an image is equal to a product of two other images. So it's actually the reverse. So, but then the algorithm involves matrix multiplication. Okay.
But once you perform those multiplications, you completely lose the original interpretation.
Sure. Yes. Yes.
So that's why this is extremely mysterious here, because multiplication is composition of linear transformations.
Yes. So
as
what?
we know, and I don't see those linear transformations.
Yes. So once we have the data, just some data, then we treat them as numerical values. I don't see the image anymore until at the very end when the code stops, and I then I want to see what image I get. So I don't stop the algorithm until the very end. I don't check where I am and what I'm seeing until the very end. So yes, there's a lot of math in terms of representation, a linear transformation, all of these things, but we're just looking at numerical values.
So
They're just,
in the intermediate steps, the meaning is being lost.
yes, I don't,
It is only apparent at the very end
Yes.
when you got.
yes. So when I work with chemists, this is what typically happens. So we have an algorithm, we have a data that's clean, processed to us by some group that's already pre-processed the data, remove some of the noise and so forth. Then we feed it into this numerical algorithm, and then we get a bunch of data. And so we plot the columns, and we get some plot of the concentration and so forth. And then we checked with the chemist and see, what are you seeing? Does this make sense? Does it make sense to have 5 pollution, or does it make sense to have 4 pollution? And what is this? Is this an error, or is this another pollution that you can identify? So then we go back and forth, and even we go back and forth, the chemist is sort of like, we're not supposed to see salt or something like that. Then, or there's something wrong, then we come back, and we even to the level of, we change the algorithm sort of specific to this data. Maybe we're not getting the right scaling because we don't pay attention to that. And at the end, what's important, you get concentration of like 1,000, which doesn't make sense. So it's not the right scaling, and so forth. So we kind of have to come back, redo what's inside the black box, and then out come a solution that's sort of that sort of makes the scientist say, okay, this makes sense, this is sort of what I expected, and so forth. So then we go by that, by his expertise.
So isn't it true that at the end of the day you want to apply some matrix valued map on matrices and you are expanding them into Taylor series, so you are dealing with matrix polynomials after all. When you have matrix multiplication, you can add them up and you can matrix polynomials and you can approximate functions, matrix valued functions with those polynomials. That's my impression.
So wait, what's your goal? You want to improve the complexity of
I
matrix?
want to understand why we multiply that. So what
So-
the end result is. So what do we do of a matrix? So when
Why
you-
do we multiply
when-
matrices?
Okay. When you smoothen it out, then it's okay.
Yes.
You apply a matrix valued function to the matrices.
People are wondering why you would multiply a matrix, and I don't know enough about image processing to give that kind of example, but.
Why you would multiply matrices?
Yeah, but
Yes.
here's another example, really, you represent people in different ages in the population as numbers in those ages. And every year, some of them go to the next stage, but some of them die, some of them reproduce new children, and so you can represent those transitions between the different ages as a matrix. And if you want to find out what happens after 10 years, you use 10 of those matrices.
Sure.
Because every time you're sort of feeding the ages of people, the numbers of people in each ages into this matrix, and out comes the number in the next stage. And if you want to do that over and over again for 10 years, you multiply the matrices.
Got it.
So that's an illustration of why you would want to do it from a different domain.
That's very convincing.
Let me make sure I understood what you said, Marshall. So you have a vector of ages.
Yes.
People in different age groups are a vector, a row
Right.
vector or a column vector.
Right.
And then you have a transition matrix that moves people from one age group to another, and also moves people into the first age group.
Yes.
People or fish or whatever, because they were born. Okay? That matrix is in fact a sparse matrix,
Right.
because it's typically sort of a diagonal and a column, if I
Yes.
remember correctly.
Right.
And 1 year, you do that transition. But you want to know what's going to happen 10 years, so you take the product of that transition matrix by itself 10 times, and then you multiply it times your vector, and that's what the population of your fish are going to look like in 10 years.
Yes.
And you're doing this not with fish in 10 age groups, but with something in 1 million age groups, which doesn't make sense now anymore, but it's a different context, but it's the idea is maybe
Yes.
similar.
Right.
I think your point is that there are many reasons to multiply.
Yes, there's many reasons.
Depends on the algorithm one
or
has
the-
in mind, and you want to concentrate on how it's done. Right?
Yes.
You should take as a given that you need.
That we need to multiply matrices. There's.
So that was the earlier talk that we did, right? Where you said why it's important to know how to multiply.
Just for image processing, one of the things you do is edge detection.
Sure.
If you have a picture of the moon, and here's these white blurs and black blurs, and our eyes are real good at saying, oh, that's a rock. And there's the outline of the rock.
Yes.
But
Yes.
when use matrix multiplication, that to find the edges of that thing, so they can say, here's an edge, here's something in here, so I won't guess it's wrong. When you're writing program. But edge detection is a big thing.
Yeah. So yeah, there's a lot of techniques for edge detection, right? How do you also segmentation? Yeah, you want to know, maybe a picture of, where's your heart, right? You want to be able to figure out in that,
And also tumors,
Yes, that's right.
which we don't want to look at still.
I don't, at least. All right, so everyone's happy with this 2x2 matrix multiplication. That's, we're just doing 2x2, 8 multiplication and 4 addition. So I give credit to this guy in 1969. So a lot of things happened in 1969. What happened in 1969?
I got drafted.
Okay. First man on the moon, is that right? 1969. So Volker Strassen found an algorithm. He said I could do it in 7 moves, right? So we had 8. Previously, we have 8 multiplications. So he said he could do it only with 7 multiplication, which is quite an improvement, right?
It's very misleading because for small n, the
Well, it
difference
depends.
doesn't look big.
What?
For small n, the difference is
Yes.
not impressive.
Sure, yeah, but
But we would like to see the formula.
yes,
For
but for math.
so that's going to be impressive.
I'm not impressed if it's n cubed minus 1.
No, it has to.
Right.
So first you can imagine n to be even, but it also work when n is not even. We could just fill it up with zeros and then even it up. So this is Volker Strassen, but his goal was actually to disprove, to show that no algorithm exists that can beat this 8 scalar multiplication for matrices. That was his goal by process of elimination. But through the process of elimination, he couldn't eliminate this one thing, and that's the Strassen algorithm. And so ready? This is, it was hard for me not to write this equation down. So these are the same elements, C11, C12, C21, C22. So those are the same element that we try to get with the standard matrix multiplication. But so Strassen came up with 1, 2, 3, 4, 5, 6, 7, these 7 steps, 7 scalar multiplication. And by adding and subtracting these 7 multiplication, we get C11, C12, and C21, and C22. It's an iterative process, okay? So not just for 2 by 2. Let's say you have, I don't know, 4 by 4, or 1F 4 by 4, but you could have, let's see, we could do a 4 by 4, then split it up, not 4 by 4, but maybe, yes. So we could split it up into, the simplest one is to have, oh, actually, I have a slide. So if you can imagine, instead of A11, A12, and A21, and A22, instead of just one value, you replace that with a 2 by 2 matrix in each of the A11, A12, A21 position. So you have a matrix in each block, so you can have matrices sitting where a scalar value was sitting before. Okay, so it's an iterative process, and you can count that it's going to take 7. So in this case, we're taking k to be equal to 2. So it's going to take 7 to 2 multiplication and this much addition. Okay. So this is actually, I think, one of the. Okay, this is the last slide actually. Yes.
You might be about to say this.
Yes.
But now that you can do it in blocks, does that mean that this algorithm is parallelizable? That you can give,
Sure, you can send different.
One
Yes.
part of the multiplication of one
Sure.
computer and another part of the multiplication to another computer, and so on, and you have 1,000 processors
Yes.
in
Yes.
your supercomputer.
Yes, that's right.
And so that makes it even faster because
Yes.
you don't have to do it
In-
one little bit at a time and then put it together.
Yes.
All these computers do it and then
Send all the solution back to you. Yes. And so, but also, there has been improvement since 1969. So, 1980, Coppersmith and Winograd. That's, I think, currently being used in our computers, in our machines. But there's recent improvement in 2010 and 2011 by Williams from Berkeley and Stanford. So she beats it quite a little bit. And so there's one thing I wanted to add is that, so Strassen wasn't an algebraic geometer, but he actually had worked as a probabilist. He has some result in probability. So he was just kind of doing this on the side, and then a lot of algebraic geometers, the type of mathematician that deals with polynomials, who likes polynomials a lot, looking at solutions to polynomials, that these 7 addition, 8 addition actually means the rank. So these matrix multiplication has tensor representation, and the number of multiplication has to do with rank. So to some of you, what I just said doesn't make any sense.
Which also means that the 7 cannot be improved anymore.
Hmm?
Which also means that the 7 cannot be improved anymore. It's sharp.
Yes,
For-
for this
for
specific,
multiply.
yes, that's right. But it's open to other problems for other dimensions. So I think I'm going to end here. And thank you. This is a pixelated picture of Birmingham without snow, so situation back to normal. So thank you for your attention.
Got a question?
Yes.
In the beginning of your talk, you used the two terms, frequency versus time.
Yes.
And with respect to sound in music, time is measured in, by the number of beats in a measure. And what you're saying is much more refined. So how much sound are we dealing with?
Well, I don't know how to answer that question because I guess for this representation, when you hear a sound, it's represented by what's the how many of the frequency.
Of vibrations in the sound?
Is that vibration in the sound, I guess?
I guess you would, yeah. All right.
Here you meant the pitch, right? By the frequency.
Yes,
The pitch of the sound.
yes.
But it's not just the pitch of
It's-
one,
It's a fully
all
expanded.
of the overtones of the
Fully
instrument are
expanded,
simultaneously represented.
Yes,
So
all
you
what's
can
the
tell the oboe
it's a
from the
combination
flute
of all.
Because it's a combination of frequencies that are related to each other.
Yes.
That's how they decompose it. Is you can recognize the instruments from the other frequencies that are played at the same time as the main pitch that the instrument is making, I think.
Yeah, again, yes. I when I run my algorithm, I don't pay attention to that, and then until the decomposition is sort of it's a black box. So it's I have numerical values, so I don't stop the algorithm at the end. You get a separation at the end. So I know the data is coming from sound signals. I know it's coming from air pollution, but we're using the same algorithm to demix the data.
I
So
believe different instruments have different signature.
yes,
spectral
that's right.
signatures.
That's right. So we can separate them.
That's what our brain also does to some
Yes.
extent.
But what's interesting is that when I take this data and try to play it, I can detect it visually by looking at the spectrogram that we get back. But if I play it, it's garbage. It's hard to reproduce sounds from our algorithm. Visually, we can detect a different instrument, but we're not there yet in terms of spitting out a data and then playing the sound that we get. That
Playing
said this
that
is,
instrument.
yes, yeah, and it's garbage. But picture-wise, visual-wise, we say, okay, that's a clarinet, or that's a drum. Yes.
Yeah, I know a man who created a 50-speaker stereo set, and he could turn on one of those speakers and listen to the cello, or he could turn another one on and hear the timpani. And when he turned them all on at once, the roof actually shook like that, you see. But it would have been interesting to see what sort of matrix that sound would.
Yeah, we can collect it, just collecting what we hear from a speaker, and then actually read off a spectrogram of,
Right.
of the timpani or whatever instrument. But you said this guy has 50 speakers, each
Right.
one playing different sounds?
Yeah, each
Okay.
could pick up different sounds in
In-
the orchestra when it was played, in any composition.
Oh, wow.
So that
So he has an algorithm that does this.
You see, he was a sort of genius. He happened to be my father.
Oh.
So, without the math.
Yes, yes,
But had he had the math to work with, no telling where he would have gone with it. So,
yes, yes.
yeah.